kind of a funny aside to introduce you to this concept of the Mesophotic zone is that when I was a graduate student and certified scientific diver, and I used to talk to people outside of the science community, and people found out I dove, they would say, "Oh, really? How deep have you been?" And what I thought was a quick, witty, and clever answer back then was, "Well, I've been to the bottom." And this was always very awe-inspiring to some people. The bottom can be 5 feet, though. Right? So I didn't do anything as extreme as this exploration of Mesophotic coral reef systems, but just to glean to how important this is, that recently, or earlier this year actually, the Woods Hole Oceanographic Institution was awarded $35 million by the Audacious Project to explore the Mesophotic zone, mainly in the open ocean, where they define that as between 200 and 1,000 meters depth. So this is an area where, going to the bottom, saying you've been to the bottom, that's where we all kind of go. We either stay in the surface of the ocean or we go to the bottom, right? If you're involved with IODP, you go to the bottom and you take core samples. You don't necessarily go there, but you take samples from the bottom. And if you're a physical oceanographer, you concern yourself with surface currents, because the surface ocean is where the wind is interacting with the ocean. But we have this whole sort of middle layer of the ocean that we don't know much about. And that's, over the last decade or so, has spurred a lot of interesting research and interesting questions. Now, Huey's definition of the Mesophotic zone, 200 to 1,000 meters, is not going to be touched by divers anytime soon. Well,
no, not me.
Not regularly, but what Clark is going to show us today is areas of 30 to 90 meters where with recreational diving you don't normally go. And he's breathing some interesting mixtures of gases to get there, and having some pretty short working dives at some of the deeper depths. But this is interesting because this is where the ocean meets the continental shelf, and look forward to hearing more about it. Now, just a little bit about Clark. He graduated with his bachelor's degree from the University of Rochester. Then he went to, he grew up in upstate New York. Then he decided to go to Hawaii for a master's and a PhD. When that was done, came back to South Carolina for a little while, and then found himself in University of Puerto Rico, where you've been since, what, 2000?
2005.
2005, okay.
Yep.
So, yeah. And he's been there ever since at the Marine Lab at La Palguera, where some of what we'll see today is right from his backyard.
Yeah, the backyard. Excellent. Thank you, Brad. First I want to thank Brad for inviting me up. It's really been a pleasure to meet and talk people and re-meet people that I met a while ago. Great discussions today, and hopefully that will lead to some kind of new project and new collaborations. And I just, before getting going on the talk, what I'm presenting today is really a kind of result of efforts of lots of different people, primarily in the Department of Marine Sciences. There were projects to fund this work on mesophotic reefs or mesophotic coral ecosystems, and there's just been a whole collection of other faculty members and graduate students, and some of these are divers. A lot of these graduate students have now moved on. And also Doug Kessling, who was at the University of North Carolina, Wilmington, and we did some of our original technical diver training with him. And he kind of became part of our group and was down in Puerto Rico a lot doing the rebreather diving with us. A lot of the photographs I'll be showing were taken by Doug and Hector Ruiz, who is a graduate of our department. And I would just add that the technical diving program that Doug was in charge of at UNC Wilmington has subsequently been closed down, and that's really a big loss to technical diving and this type of research because it was a great resource. And I also want to thank, I was fortunate enough to be asked to lead a chapter in a new Springer book, which is part of the Coral Reefs of the World series. And so some of the figures and concepts I'll be presenting kind of came out of work on that chapter, and I just want to thank my co-authors on that, including Stan Locker, who's from the College of Marine Science, Jody Webster in Australia, and David Weinstein, who got his PhD in Miami, and he's doing some postdoc work over in Israel now. There we go. So quickly, as Brad kind of mentioned, this term mesophotic is sort of a recent terminology, I believe. And we all know, I mean, going back for several decades, people have been studying reefs, at least kind of modern studies. Of course, people were studying reefs way back with Darwin and Dana, but using scuba to access these environments. And if you're looking in shallow environments, you can easily access, it's warm, clear water, and you can get there with traditional scuba techniques and do all sorts of good studies. As we get a little bit deeper, it becomes a little bit harder to get to. And so they're obviously in the deeper parts of these reef systems, or deeper, if the whole reef may be deep, there's been much less work on those environments. And in this figure, using to access these reefs, and kind of big ROVs and submersibles are typically focusing much deeper, thousands of meters. And so we have this kind of in-between zone that's received less focus, both kind of research focus and to some degree even funding focus, focusing specifically on these habitats. 10 years ago, 2008, there was a workshop following the Reef Symposium in Fort Lauderdale, and that was sponsored by NOAA, and that was to get people together and talk about this depth zone, I guess, and come up with some ideas of research strategies. And this is really where this term Mesophotic coral ecosystem came about. The term Mesophotic was being used, and it was really where it was kind of formalized and defined, I guess. And there were several papers that came out of that. Stan was at that workshop and was kind of led the geology group. This is just an abridged version of what the term means. So mesophotic coral ecosystems, light-dependent corals and associated communities found at depths ranging from 30 to 40 meters to maybe over 150 meters. So it's a little bit broad and ambiguous on what they are. So it's benthic cover and depth. So there really isn't any hard criteria, either what's the upper and what's the lower zone. It's sort of gray. Actually, the lower zone, is the end of it, is probably more defined, as it's where these organisms no longer exist. I mean, the base of the photic zone, where these types of organisms cannot occur. In some cases, these may be extensions of shallow reefs, so just extending deeper, especially at shelf edge settings, or they may be completely isolated and not directly connected to shallow reefs. And some of the early reasons for looking at these environments was that obviously there's different organisms, and they found found new species in these deeper settings. The extent of these mesophotic ecosystems may be equal to the extent of shallow reefs. So we think about management and protection. These are big areas that need to be sort of included and incorporated into those plans. And there's also been this kind of back and forth idea of refugia, in the sense that these areas are deeper, typically further offshore and further removed from people mostly, but also maybe the influence of storms or influence of bleaching events. And that's something that people sort of go back and forth on. So I'm not really going to get into these things. That was sort of some ideas of why to focus on these settings. And I'm going to talk more about the kind of the geology behind these settings. And so again, they're defined by the benthic cover and the depth. And so when we describe the geology behind these settings, it's essentially, what is forming the structure that these organisms are recruiting to. And an important influence on that physical setting is sediment dynamics. And the geology and geomorphology are kind of control those factors. In a very large scale sense, just looking at the general tectonic setting forms the kind of the foundations of these systems, as well, of course, shallow reefs. And just in a broad setting, you've got active versus passive margins. And so over in our region of the world, of course, the Florida Shelf, Gulf of Mexico is, of course, a passive margin, versus down in the Caribbean, that's primarily active margins, and I would kind of lump active and insular margins together, in the sense that you come up with some different basic characteristics. And passive margins with very broad shelves that tend to be deeper, and active insular margins, much narrower shelves that are generally shallower. So along an passive margin shelf, a broad shelf with typically a deeper shelf break at maybe 70 meters or more, so you've got a large area that's at mesophotic depths. So more area, potential area for MCEs. Though the MCEs in these areas are typically going to be located on some topographic high, some relic feature. They're not necessarily going to be all over here because those flat surfaces are also good places for sediments to accumulate. And so the little arrows I put in here are just sort of kind of indicating directions of sediment transport. The passive margin MCEs, maybe the broad shelves, maybe they can be further removed from terrestrial inputs, and they may be more isolated from shallow reefs. If these relic reefs are popping up way out on the outer shell, they may not have kind of a shallow counterpart to them. And this, like the MCEs that have been described around the Gulf of Mexico and on the West Florida shelf. So this is from the Coral Reefs paper from the special issue in 2010. So the yellow areas indicating all of the depth zones, I believe between 30 and 100 meters. But the MCEs really are much more restricted than that, occurring on topographic features, and many of those are relic features of probably different origins. Versus active and insular margin shelves that are typically going to be much narrower, have a shallower shelf break. So here the MCEs are going to be more on slope environments. They're going to be closer to potential terrestrial inputs. And they're generally going to be more extensions of shallow reef systems. So going a whole gradation from a shallow shelf edge reef down into the mesophotic zone. So this would be more like the systems that we're looking at along the shelf margin of the Puerto Rico Virgin Islands platform. We do have some deeper shelf areas, so these don't get that deep. Typically maybe up to about 50 meters, and these are just kind of a few really sort of isolated occurrences of, say, kind of well-developed MCEs up on the shelves. Where are we? There we go. And so these are just some bathymetric images off southwest Puerto Rico, where we do the most of our work. And these blue multi-beam images, I'll be showing the shading is slope. So darker areas are steep and the lighter areas are more gradual. So the contours may be hard to pick out, but basically the shelf, this is a 20-meter contour, so the shelf break is a little more than 20 meters. And most of the areas we're looking at are along the insular slope. Or like a place like Jamaica, I like this figure. You see it definitely is a narrow shelf and kind of right directly connected to shallow reefs. And this comes from the kind of classic works from Garreau in Jamaica, and way before they were doing mesophotic, before mesophotic was cool. So, I mean, they didn't put some arbitrary line here. They were simply describing the reef from the shallow point, the reef crest, down to where there wasn't any more coral, and just describing the whole system. So what I'll be describing today is sort of looking at a range of different sort of geomorphology, geomorphic settings. These are different sites that we visited over the course of 3 cruises, and most of this is kind of one, maybe visit once, or on subsequent cruises we may be able to get back, we may have been able to get back to the same site, doing sampling, photo transects. Our primary place that we do our research is right here. Our lab is right, a little island offshore there. So we've done a lot of kind of more recurring, repetitive work here, and all these other arrows are sites we visited on cruises. On these ones in green are kind of, these will come up in subsequent images as examples of different geomorphologies. We use we have pretty good multi-beam bathymetry, not everywhere, but where we have it, it's very useful is that we can kind of identify structures, features that we want to dive at. Use ROV to kind of do some scouting and a little bit of surveys, but again, importantly, using rebreather diving to get to these environments for sampling, photo surveys, putting in instruments, and so forth. And the technical diving has been really important to our work, and it provides having people in the water gives you a perspective that you just can't get from a screen on an ROV or in the couple of submersible dives I've been on. It was those ones where you're looking out a dinner plate size windows, so you sort of really lack a perspective. And again, you're able to do really precision photography and sampling and so forth. Obviously, there are trade-offs, so we're very limited amount of time we can spend there, and just the logistics of it are difficult, but it's been key to accomplishing the work that we've done here. So first, in those different areas I showed on that map that we visited, we can kind of divide them up just very generally into shelves versus slopes. And in shelf, I'm just talking about low gradient settings, either kind of the outer portions of insular shelves or the tops of kind of planar tops of isolated banks. So roughly horizontal, maybe gently dipping, and these are typically low relief, low rugosity areas with a very rubbly substrate. When I talk about MCE development, I'm thinking mostly of corals. So the C stands for coral, and as a geologist, I'm also interested in stuff that may be producing framework and structure. And so on these platforms, it's kind of patchy development of MCEs, and they're typically focused on any kind of topographic feature, as with shallow reefs also. Kind of one unique example on the Puerto Rico Virgin Islands platform is on the shelf south of St. Thomas. And again, this is sort of different than other areas because it dips and kind of the shelf dips into mesophotic depths before reaching the shelf break. And so we're looking at depths primarily in like the 30 to 40 meter range, and these are sites that Tyler Smith at the University of Virgin Islands and his group have been working on for several years. And these settings are dominated by Orbicella, and they can have pretty high coral cover. But these are unique. These are essentially the same corals that are occurring in shallow reefs. So this is just providing a little bit deeper area for these corals to occur. But when you go to deeper platform settings, this is Bajo de Seco, which is in the Mona Channel to the west of Puerto Rico. So we're looking at the top of it here. This is the 50-meter contour and the 100-meter contour. So you've got this broad, pretty just gently dipping surface up there, so able to catch a lot of light. But when you get to beyond about 50 meters, you're not going to have a lot of those massive corals, really very few. And it's much more platy agariciids that are the dominant coral. And so you see on the surface here, we do have corals, the agaricid corals, and a lot of other stuff, sponges, algae, but it's all a very rubbly substrate. You're not building up structures there. One thing that is very common on these platforms and at the base of slopes are rhodoliths, and they're a really important substrate that stuff is recruiting onto. This is one that we collected, if I can go back, on Grappler Bank, this little yellow spot just to the south of Puerto Rico there. The top of it is at over 60 meters, about 60 something, 63, 64 meters. And again, it would have sort of a surface like this, a rubbly surface, and a lot of these rhodoliths that you can see that the corals recruit onto. And on these platforms, a lot of the corals are just attached to rubble. When we would sample them, you could just lift them up off the bottom. So it's just a loose kind of a pile of this stuff. And when as we were having these discussions yesterday, so here's a rhodolith at 64 meters, and the traditional origin of these things is that they're getting tumbled around. But this thing isn't getting tumbled around now, I wouldn't expect. I mean, it's got coral living up on top of it. But it made me think of the ooids we were talking about yesterday. And this thing is at the top of this bank. And if this is maybe these rhodoliths are more reflective of past conditions and lower sea levels, is that's when they were getting rolled around. So those are shelf settings. And when we go to slopes, we have kind of a different set of characteristics and sort of challenges for the MCEs there. So slopes referring to the edges of the margins of insular shelves or the margins of isolated banks. We've noticed along the Puerto Rico Virgin Islands platform that the slope gradient is very closely related to sort of the prevailing wave conditions. And of course, anytime there's some subtle breaks in slope, those are important areas for MCE development. So I've got here slope settings present unique challenges, but I also should add it's also not just challenges, but advantages as well. So obviously when we, especially in the mesophotic zone, light starts to become a limiting factor. And so as we increase slope, we're decreasing the availability of light. And also there's potential of downslope bedload transport, especially if you have shallow reefs above you that are producing sediment and shedding sediment. On the other hand, that slope also allows sediment to be swept by you, so there's also advantages to that. And when we look at these slope settings, we've just very qualitatively divided them into a few different categories. Steep slopes, roughly 30 to 70 degrees, low gradient slopes, less than 30 degrees, and wall habitats are kind of anything over 70 degrees. And so I mentioned how the slope gradient changes, and it appears to be related to degree of exposure to the prevailing sea conditions. So this is the direction prevailing of waves, and you see predominantly from the southeast, and this is from data from a buoy off of Ponce. And we can see this is the shelf margin off of Parguera in southwest Puerto Rico. These areas that are kind of more facing into the prevailing seas have a more gradual slope. They've got this broad, in this instance, this kind of broad terrace at about 80 to 90 meters versus just on the other side here that's just facing a little bit in the other direction, much steeper. You see the contours bunched up together. And also in these steep sections also often display kind of landslide scars. So at some point they were kind of calving off pieces. And the figure on the right is just showing the profiles in different areas along the shelf margin from more exposed areas with a more gentle gradient. You can see once again the pronounced terrace here at 80 to 90 meters, and then more sheltered, facing more, in this case, more kind of southwest, are consistently much steeper. And this is a pattern that occurs along the shelf margin. You can kind of see it, and image I know is kind of narrow along here, but you can see where this terrace comes out, and it basically just shows up on the areas that are facing into the southeast along the gradual slopes. See it kind of pop out again here, and then these other areas are much steeper, and there's little landslide scars along those steep sections as well. And we see different types of MCEs along just based on the slope gradient. And this is just showing that it not just off Parguera, but this is this is El Seco, kind of south, just to the east of Vieques. And once again, we've got a kind of protrusion of the shelf, looking at the shelf edge, and into the southeast, gradual slope, broad terrace down here, versus just around the corner and this other side, much steeper profile. So low gradient slopes are kind of sort of like the platform or shelf settings that I described before. So these are kind of low relief areas. They tend to have more loose sediment cover. Kind of, again, once again, sort of a rubbly substrate and typically or more scattered corals. And just another image of this, you can see a lot of more sand cover. There's a lot of other stuff on there. I'm kind of focused on the corals, but sponges and algae. And kind of zooming in, this would be what the cover typically looks like. Again, when in these deeper settings, the overwhelmingly dominant coral are different agariciids, and really beyond about 60 meters, it's mostly Agaricia undata, along with a whole bunch of algae, and there'd be algal nodules and sponges and so forth worked in here. Now I mentioned this terrace at about 80, kind of starts at 80 and slopes very gradually out to 90 meters. And so if light is the limiting factor, this terrace should be a spot where corals would want to be to capture the most amount of light. But we have to remember that up here, there's all sorts of carbonate material being produced up here that's coming down this slope. So it's kind of a trade-off between those two factors, kind of light versus sediment. And so when we get down to this terrace, it's more of a sediment accumulation zone. There's very little coral on this terrace, even though it's flat and you'd be able to capture a lot of light. And so this is, these little guys are a bunch of rhodoliths, all these little nodules down here. So that it's more, the low gradient is less conducive to corals. And I think part of that is we have to think about the corals that are living at these depths are primarily platy corals that really don't want to be on just a flat horizontal surface. They much prefer to be on a slope where they can easily kind of shed and get rid of sediment. You know, if this were at 40 meters, we might see a bunch of cellas that are growing up there. But along these kind of more gradual slopes, anywhere there's some little nick or change in the gradient, you can see a change in the cover. And this is, once again, off of Vieques, and this is sort of an in-between slope. I just want to point out this slightly darker area here and this little strip. And, you know, just from the multi-beam, we can look at that. We're like, well, let's try to hit this little spot and see if there's stuff along there. And right along that little strip, which may be a meter, a couple of meters sort of drop, is where all the coral is. You can see lots of real sandy below here and kind of sediment above, and there was just a strip of really high coral cover, right where there's that subtle little change in slope. And just kind of zooming in on that, and again, primarily Agaricia undata. And then along steep slopes look very different. So this is off Pargera, and on these steeper slopes, they tend to be much more irregular topography, kind of pronounced buttresses and narrow sand chutes, and this is where we see our highest coral cover and cover of a lot of different types of benthic cover. So the sediment that's either produced higher up on the slope by shallow reefs, or that's being shed off the production down here, gets funneled into these grooves and carried out of the system. It's on these steep slopes that we, again, see what I describe as the best developed MCEs. So they've kind of in the, it seems to be the sweet spot in terms of light and sediment transport or sediment accumulation. And just a few examples of that. These quadrants we use are 40 by 60 centimeters. You can see in some cases just almost continuous coverage. So steep slopes show better development of MCEs in terms of coral, but there's also a limit to that. And as soon as they go too steep to kind of vertical, then the light becomes too limiting. And actually sediment becomes a problem. This is just an image. This is over in Mona off to the west of Puerto Rico. And once again, the 50 and 100 meter contour, and you can see this is basically just a vertical wall along here. And so showing this figure again, so there's lots of other stuff on this wall, lots of black corals and other gorgonians and soft corals, algae, but hard stony corals very limited on here. Or other light, well, I shouldn't say that. Stony corals are limited. And just a couple images of that. A couple, I guess there's one here. There's another guy up here. So a few corals that are kind of clinging on there, but mostly it's other types of organisms, or there's just really kind of bare rock with maybe sort of an algal turf on there. So this is where light is probably, you kind of become too steep where maybe light is limiting. And interestingly, sedimentation is also a problem, which you might not think on a steep vertical wall, but I kind of envision it like a slow waterfall. It's these intermediate slopes. Sediment can kind of get channelized down it, and so you can have these protrusions that are conducive to coral growth. And as it gets too steep, now it's just coming over everywhere, and any little place that sticks out tends to accumulate it. And you zoom in and do transects on these walls, and and the sediment is primarily this guy, all these halimita and stuff that's constantly breaking apart and shedding, producing fine-grained sediment, and every little pocket, everything is kind of getting accumulated or buried by this sediment, even on a steep wall. And where there's a little terrace sticking out that could potentially provide some more light, again, it's more rather than the corals concentrating on there, they don't go there because they would quickly get buried. So they might try on the outer portions more of those terraces. And you can see it's very fine-grained material that's easily kicked up as we swim by it. So one feature that's kind of common around the Caribbean, on margins in the Caribbean, is there's sort of a deep drop-off, and which I labeled, this is off Puerto Rico again, which in this figure I've described as the deep escarpment, where even where the slope is very steep, it gets even steeper, if that's possible. I mean, it just goes to a near vertical, it's a deep vertical wall, and it's a recurring feature around many Caribbean margins. And it doesn't always occur at it's not the same depth everywhere. So off of Parguera, it's at about 90 meters is the edge of it. So we'd have pretty good coral cover basically down to here. And once it goes vertical there, it seems like the light is too limiting, and there's virtually nothing beyond that. So here's very extensive coral growth down at 76 meters. But if we go over that wall, and I'm sorry, this is a very fuzzy image from the ROV, we get basically no coral. So that's more of a light limiting factor. We don't have bathymetry for the north coast of St. Croix, Cane Bay. But this is a sketch from Dennis Hubbard, and there that kind of change to the deep drop-off occurs much shallower. So it's at about 55 meters. And so in Cane Bay, we have very lush coverage down to that deep drop-off. And once you go over that, again, you're into that deep vertical wall, and there's virtually no coral there. So at, once again, 55 meters in St. Croix and 68 meters once we've gone over that steep drop. And remember, in that image I showed in Parguera was at about 76 meters. I think the difference there is just where the change in geomorphology is. That is where it changes from, goes into that steep wall. In those Garreau papers from Jamaica, they described the feature as the final drop-off. So I mentioned sediment dynamics a couple times, and in order to try to get a more quantitative estimate of sediments and sediment movement, these are two of our kind of recurring study sites off of Parguera in southwest Puerto Rico, kind of a low gradient site over here, broad terrace down here, and then more of a steeper, very almost not quite vertical, but a steep slope, about a 40-degree slope at this other one. We did repetitive photo transects along these. And one thing, those were basically meant to look at changes in the benthic cover over time, you know, different organisms and so forth. But I also used those just to look at them and see what is the changes in the sand in the transect. So each of these bars represents the percentage of sand in a 10-meter transect, a 40-centimeter high, 10-meter strip. And the dark area, the dark bars are from the kind of low gradient site, and the lighter gray is the steeper site. So in general, the low gradient site has a greater percentage of sand, which is not that, which makes sense. But also, importantly, it changes every time. So sediment is moving through there, and it's constantly kind of getting moved through there. You don't need a big storm for sediment to move. It's either kind of slowly creeping down or something is triggering these movements. And just as an example, so here's a little strip from one of those photo transects. So this is June 2009, and we can just see how this changes over the course of a year. See kind of algae growing, and then kind of an influx of sand, and then kind of return of some algae. So this is constantly, and this isn't like a big storm or something that happened. This is just, you're on a slope and there's constantly, everything is slowly sliding down there. We also put some just basic sediment traps out there to try to put some more numbers on it, catching both just the slow background settling of material as well as that downslope bed load transport. The vertical traps, the sediment traps, are just showing there's very low sedimentation rates at these sites. So this is less than, for the most part, less than 0.5 milligram per centimeter squared. If we were up on the shelf, kind of closer to shore, our similar traps would be accumulating like 10 to 20 milligrams per centimeter squared per day. And the other thing is that, so each of these bars, once again, represents an individual trap at two different sites. And note that both kind of within and between the sites, they're basically all recording about the same thing. We've got kind of something happening here. We have higher rates, but their rates are low and they're pretty uniform among the different traps. Versus the bed load traps that are capturing what's sliding down the bottom, the rates are all over the place. And now we're looking at hundreds of milligrams per centimeter per day. And so material is constantly moving down through there, and it's highly variable, both in time and space. So at a particular site, one trap can be getting hundreds of grams of material, and another trap not too far from it may not, getting a fraction of that. Which isn't surprising, as this stuff is coming down and getting directed to different areas. But the downslope transport is again orders of magnitude higher than that just kind of slow background settling, vertical sedimentation through the water column. So the stuff, the benthic fauna that's living there, has got to deal constantly with material being flushed down the slope. And then what's driving this, we didn't have instruments out when we had the sediment traps out. And this is just a modeling of wave orbital velocities at different depths. And there's not too much we can say about this. This is using wave data from a buoy off of Ponce, just to the east of our lab. And these velocities are very low. Whether or not they're actually able to move sediment is debatable. The the scale in this upper graph at 20 meters is much higher. Obviously, the orbital velocities are higher at the shallower depths. And I would just point out that we do have this sort of peak kind of in October and November, which may explain these peaks in the vertical sediment traps. So maybe stuff was getting stirred up on the shelf and kind of sent off the shelf and then slowly settling down to the deep traps. It may explain some of these bed load traps here, these high values, but not all of them. So again, the bed load is a whole different animal of what's driving this, and maybe there's other currents or internal waves that can be moving that material around. And those questions about sediment dynamics led to some discussions with Kurt Storlazzi and his group, his USGS group that's based out in Santa Cruz. And we ended up, they were able to bring some equipment out, and we were able to put it at our kind of steep site. This is at a depth of about 55 meters. And they had a whole array of devices on this thing, including an ADCP, a couple different turbidity sensors on there, temperature. We also put in a thermistor array extending from about 58 meters or so up to the surface. So this went in August of 2017 and came out in December of 2017. And of course, there were a couple of events that happened in between there. So of course, the hurricanes came through, Hurricane Irma and Maria came through, and so this instrument package was sitting out there during those. And very fortunately, it was still sitting out there when we went in December, and everybody was very relieved to see that. And I don't really have the background or expertise to go into this, and this is from a AGU poster that Olivia Sheraton did. And this is being worked up in Kurt is writing this up, I think, for Geophysical Research Letters. But just to point out a couple of quick things, this is more kind of a teaser for upcoming papers. The top is wind, and you can see where they've highlighted the passage of Irma and then Maria 2 weeks later. We got the shelf wave heights, and these are actually from a shallower ADCP up at about up on the shelf. You can see the waves here where the passage of Irma went more to the east of Puerto Rico, affected more of the Virgin Islands. Maria, of course, directly impacted Puerto Rico, but much further east, on more the eastern end of the island than where our instruments were. But we see the peak in waves here with the passage of Maria, and those are getting up to about 5 meters high. And the interesting thing here is look at the temperature. Notice here's Irma, and we seem to get sort of an upwelling with these cooler temperatures coming up, and then a very dramatic spike here lined right up with the passage of Hurricane Maria. In the southwest, with the passage of the storm and rotation of the storm, the winds were primarily coming out of the northwest. So it's primarily blowing offshore, so probably a pretty pronounced movement of surface water offshore and allowing for this pretty dramatic upwelling here. There's different current measurements, which honestly I don't completely understand. But I do want to point out this bottom one. I just kind of noticed something in this last night, and I was talking with Ilse about this earlier, but these are backscatter. The the kind of reddish orangish color is optical, and the green is acoustic backscatter, but obviously you see this big spike right with the passage of the storm. So even at 55 meters depth, stuff is getting either transported off the shelf or stirred up even at those depths. And then notice with this acoustic one, so here's pre-storm kind of background conditions, and notice this one is elevated for several weeks before it goes back down to kind of pre-storm or background conditions. We weren't able to get back into the water until down in here somewhere. Well, actually, it was December when we pulled it out. So, I mean, this will turn out to be a very unique data set to have these things out there with the passage of a major hurricane and to get this full water column from surface down to over 50 meters. And again, this is stuff that Kurt and his group are currently working up. I know I'm kind of running out of time, but quickly, so we know the term Mesophotic coral ecosystem kind of conveniently and purposely avoids the term Mesophotic reef because we don't know if they're really reefs. Remember, it's just defined as benthic cover, whether there's coral and coral-associated organisms. We know a lot about shallow reef framework from looking at fossil reefs, fossil quaternary reefs, coring into shallow reefs. Saw the great collection of cores over at the USGS today, and so you can look and see the same corals we see on the modern reefs and look at accretion rates, but we don't really have a similar understanding of deep mesophotic systems. When we see images like this from Virgin Islands, you see these orbicellas, well, that's probably a pretty good indicator of what the structure of these features are, though you don't know how much accretion there has been, or if they're just a kind of a thin veneer. This is deeper. We can kind of see this buildup of platy corals, but we really don't have any idea of how long that represents. So there's been some work looking at coral growth rates. This, again, is from the Virgin Islands. Orbicellas show these deeper ones in the 30 to 40 meter range, much slower than shallow ones. So we wanted to try to get at that, both see, are these MCEs just thin veneers over relic substrates? And if there's accretion, what are the accretion rates? And so these are different sites that we've done some coring, just focusing in on one of these sites. We're kind of looking at the top of this sort of deep spur here. This is our drilling vessel and coring rig, which is the same stuff that's been used for decades, just a hydraulic power unit. Our drill head, this pipe was just something we were using for something else. But this is just open hole coring, so drill bit, drill down, pull it out, put an extension rod and go back in. We've got about 300 feet of hydraulic hose there. It's kind of tricky to get positioned over these areas on the slope. And we go down, we have kind of limited bottom time, but try to get a core from down there. And we've got a few of them. What the stuff is made of, obviously platy corals, very thin. These are less than centimeter. The angle of these corals is the way they were growing, so that's kind of the in situ position of these things as they're accreting. But a lot of what we recovered is this more sort of nondescript stuff of coral algae and very well lithified micrite, microcrystalline carbonate. And that's shown here. So this is just this kind of nondescript carbonate mud, very hard, well lithified, very slow coring through. I kind of refer to this as autochthonous micrite, just meaning it formed in situ. And some people will call these microbialites, and they think there's microbial activity that helps the precipitation and lithification of this. And if you were to look closely at this, you can see sort of little different colorations, and this is a thin section view, and maybe kind of different surfaces that may imply kind of microbial activity. But the important thing is that this is a major part of the structure down there. It isn't just sort of filling in pre-existing voids, it's forming parts of the surface, and other stuff is recruiting on this. This is an important hard substrate that corals and other fauna are recruiting onto. We've radiocarbon, these are the descriptions of the cores. You can see we're not able to get very deep with limited time, and if you're coring through that micrite, it's very slow going. When you're going through coral is much easier, it goes much faster. These are radiocarbon ages. So in these short cores, we're still able to go back 1,500, 2,000 years, and we get accretion rates, variable going up the core, but an average of about 0.3 meters per 1,000 years. So that's extremely slow. just showing a few other logs. We had some more massive corals here, but both of those we could tell have been turned over, so probably transported down the slope. We've dated that autochthonous micrite. This short core, just 25 centimeters or so, goes back 4,000 years. And this stuff is accreting extremely slow. I dated 2 samples kind of right next to each other, and they came out with virtually identical radiocarbon ages. And you can see going up the core where we dated a couple, you get younger as you go up. So it seems like this stuff is actively kind of forming and accreting at these depths, even though it's certainly getting detrital material in there as well. So 0.3 meters per 1,000 years versus, in this figure from Dennis Hubbard, this is just showing accretion rates from 0 to 25 meter water depth, whether it's massive corals or a Carpa palmata. The accretion rates are kind of all over the place, but basically an average of about 3 meters per 1,000 years. So if this goes to 25 meters, between 25 meters and 50 meters, there's a big change. Our accretion rates are an order of magnitude less. So whether that's, there's probably light, temperature limitations that are changing that. So that is really, to me, that's mesophotic. There's a big change in there. And so that also means if there's very low accretion rates, that means the topography we're seeing is mostly relic. This stuff isn't building big structures. So as we see these kind of deep buttresses here, or this terrace down on the slope, that's probably reflective of past conditions. And just looking at its position, relating it to sea level curves, maybe this terrace is about 14,000, 15,000 years old, left behind by meltwater pulse 1A. Those deep buttresses may be younger, and left behind by meltwater pulse 1B. And then just equating them with this different version of a curve, so maybe 14,000 to 15,000 years ago, maybe 11 to 13. And we know from coring of Dennis Hubbard that these shelf edge reefs start about 10,000 years ago. So part of our coring, we were wondering if we could get through that 2 relic stuff, but we were still sort of in the mesophotic cap on top of that. So I think I pretty much used up my time. These are just sort of repeating what I've said so far. So I'll stop there to leave a little bit of time for questions.
We have one question, but I want to open up to students first. If any students have questions.
Yes.
So, since these are highly light-limited environments, does that mean that these coral reef ecosystems require a certain level of kind of surface production to be raining down, or do they just slow down their metabolisms accordingly?
It's a little outside of my area, but I know that they, in different work, that they may become more, what do I want to say, more heterotrophic with depth, so depending a little bit less on zooxanthellae, so they do seem to see changes in that. And certainly there's probably, the shift from massive to more platy corals is probably a reflection of it's harder to produce carbonate at those depths. So you're not calcifying as much, you're spreading out and becoming very thin and delicate. So there are certainly, Michael Lesser, they've worked with like Montastria cavernosa and saw changes in their sort of how they get their nutrition with depth. Yeah.
So I was wondering about the water motion regime down there, because you see these like, snowfall accumulations on this vertical wall, and I always had the impression that there were a lot of longshore currents in these types of habitats. Is that not the case in most of the places you've been?
No, I mean there can be pretty strong currents, and those sediments are probably just like little pockets. I mean little kind of micro calm zones, And also they can be a little bit sticky, a little mucusy stuff on there that captures it. But I mean, it's easy when I don't know if you notice in some of those pictures, I mean, if you're kicking your fins by there, it's easy to kick up stuff. So I don't know, so some of that may be the nature of the sediments, or maybe the currents are just enough off the bottom that they're not necessarily resuspending, but certainly there can be very strong currents to the point that you're seeing, you know, soft coral, you know, gorgonians and stuff that are bent over, you know, at depths of 50, 70 meters, there can still be very strong currents. What we don't know is how effective they are. We haven't, well, like with the instruments that Kurt had in there, we'll have a better idea of what strength those currents are, and then relate that to sediment movements and so forth.
But that's not a major variable structuring the communities, you don't think? Because, I mean, the slope angle is something I've never really thought of before. I didn't realize it was so variable, and that's interesting. But how that interplays with, you know, wave exposure or currents and...
Yeah, I guess we don't have an idea of how that, you know, the changes in the slope angle is all just very descriptive, and how that also, how other factors change, like the energy of the environment, or how that affects currents, or how internal waves are coming through. That, I don't know, and that would take, so that's just one, so like the measurements from the USGS suite is just one spot and one type of morphology. You know, some of those questions we would need a couple different arrays in different settings, so what's happening at the same time at a few different places. But certainly there is definite, the water column isn't just stagnant by any means. There's movements